from GMRP Gradual. In this video lesson, I am going to discuss about the sketch the composite video signal as per ISI specifications. Next, state the need for front porch and back porch in blanking pulses. Next, state the necessity of equalizing pulses and serrated vertical synchronizing pulses. Okay. So, first of all, so previous class we have discussed about the formation of picture and state the need for horizontal and vertical scanning and state the frame and field frequencies and vertical and horizontal synchronizing and blanking pulses, and we have also discussed about the composite video signal, different pulses in composite video signals. Okay. So, in this class, we are going to discuss about the composite video signal as per the ISI specification. Okay. So, this is the diagram of composite video signal as per ISI specifications. Okay. So, actually, in composite video signal, we have different pulses are there. So, there is a peak white level, it has a peak white level, black level, blanking level, darker than dark level, whiter than white level, and picture details. So, all these pulses are shown in this diagram. So, in that, so actually, the composite video signal means it is a video signal that contains the camera signal, blanking pulses and synchronizing pulses is known as a composite video signal. Okay. So, what is a composite video signal? It is a video signal which consists of a camera signal, blanking pulses and synchronizing pulses is called as a composite video signal. So, in that, what is a camera signal? So, camera signal which corresponds to the desired picture information or which carries the desired picture information. Coming to the blanking pulses, to make the retrace invisible, we have to apply a blanking pulses are there. Next, synchronizing pulses. So, here to synchronize the transmitter and receiver scanning, we are using here synchronizing pulses. Okay. So actually the picture information, that means the video signal is not transmitted alone. So, along with blanking and synchronizing pulses will be transmitted. Okay. So, the two signals are blanking pulses and synchronizing pulses. Here, the blanking pulse is used to make the retrace invisible. Coming to the synchronizing pulses, to synchronize the transmitter and receiver scanning, here we have to apply a synchronizing pulses. Composite video signal means a video signal that contains the camera signal, blanking pulses and synchronizing pulses is known as a composite video signal. In composite video signal, we have three types of signals are there: camera signal, blanking pulse and synchronizing pulses. Okay. So, this is about what is a composite video signal. Okay. Next, in that composite video signal as per ISI specification. Okay. So, this is the diagram of the composite video signal as per ISI specification. So, in that the details of three different lines from different frames as a composite video signal. Okay. So in composite video signal, we have a different pulses are there. What are those pulses? We have already discussed in the previous class. So one see here, we have a camera signal, blanking pulse and synchronizing pulse. So the combination of in video signal, the combination of camera signal, blanking pulse and synchronizing pulse is called as a composite video signal. So here the details of three different lines as a composite video signal. Okay. So here combination of these three different lines. So here it has a synchronizing pulses. In that again we have a horizontal synchronizing pulses and vertical synchronizing pulses. Those are there. But the mainly the composite video signal consists of a camera signal, blanking pulses and synchronizing pulses. Okay. So in that we have synchronizing pulses. This is the picture details, that is the camera signal, and synchronizing pulses, blanking pulses, synchronizing pulses and camera signal. So here the details of the three different lines as a composite video signal, that is shown in this diagram. Okay. So this is the composite video signal as per ISI specification. In that we have a different pulses are there. Okay. So each and every pulse, it has some value. Coming to the peak white level. So here the peak white level is 10 to 12.5% of the maximum value of the signal is a peak white level. So here the maximum whiteness that can be handled by using this video signal is known as a peak white level. Next it has a black level. So black level is at 72% of the maximum value of the signal is called as a black level. So here the black level is used for separating the blanking level from the picture information, and next one is a blanking level. So this blanking level is at 75% of the value of the signal, and the maximum value of the video signal due to picture details is 75% here. Above this blanking level, the picture is fully black. Next, blanking pulses are added at the 75% of the read level to make the retrace lines invisible, and the synchronizing pulses are also added at 75% level, is known as a blanking level. Next, coming to it has a darker than dark level. So the amplitude range of the video signal above the blanking level, that is 75 to 100% is called as a darker than dark level. So this amplitude range is used for the synchronizing pulses. Next we have a whiter than white level. So that is 0 to 10% of the amplitude of the signal is called as a whiter than white level. So here this amplitude range is used to accommodate excessive bright spots in the picture without causing the amplitude distortion in the modulator. And next we have a voltage levels, pedestal level and pedestal height, and we have a DC components. Okay. So these are all the different pulses in composite video signal. So next we have, so once again you see this diagram and note it down as so next topic, what is the need for front porch and back porch in blanking pulses. Okay. So actually the blanking pulses can be divided into 3 sessions. So actually the blanking pulses range is 12 microseconds, and that is divided into 3 sections. They are front poach, H-sync pulse and back poach. Okay. So in that front poach has 1.5 microseconds and H-sync has 4.7 microseconds and back poach has 5.8 microseconds. So overall the width of the blanking pulse is equals to front poach, synchronizing pulse and back poach. So this is the overall diagram of the horizontal synchronizing pulses. It has a front poach, horizontal synchronizing pulse and back poach. So here the front poach has 1.5 microseconds and the horizontal synchronizing pulse width is 4.7 microseconds and the back poach has 5.8 microseconds. Okay, here 1.5, 4.7, the width of the synchronizing pulse is 4.7 and horizontal front poach is 1.5 and back poach is 5.8 microseconds. So in that front poach, so the front poach function is the horizontal synchronizing pulse will start 1.5 microseconds later than the blanking pulse. One see here, after the blanking pulse, here we are taking everything is in microseconds. So the horizontal synchronizing pulse will start at 1.5 microseconds later than the blanking pulse. So see here, 1.5 microseconds later than the blanking pulses. So this period is known as a front poach. Okay. Next, the width of the front poach is here the width of the front poach is 1.6 microseconds with a tolerance, and the width of the front poach can be from 1.3 to 1.8 microseconds. Okay. So the amplitude of the front poach is at a blanking level, that is 75% of the composite video signal, and it is inserted between the end of the line and the leading edge of the line sync pulses. So during the front poach, the video signal will reach the blanking level which is fixed. Okay. Whatever the level of the picture level at the end of the line, the sync pulse always starts from fixed amplitude level. Okay. So next, this is about the front poach. So here, see here. So actually, even a front poach or all synchronizing or blanking pulses will be added at the after the 75 to 100% of the amplitude of this level, they will be added. So in that, here we are applying front poach is added at 1.5 microseconds and the horizontal synchronizing pulse is 4.5 microseconds and back poach is 5.8 microseconds. So here the end of the scanning line, here we are adding a front poach. Next, here also same. End of the n+1 scanning line. Horizontal retrace blanking pulse 12 microseconds. Next, coming to the back poach. So here, so actually the horizontal synchronizing pulse will terminate about 5.76 microseconds, that is 0.09 henries before the end of the blanking pulse. Okay, this is termed as a blanking pulse. So here the horizontal pulse will terminate at about 5.76 microseconds. See here 5.8. So 5.76 microseconds. So before the end of the blanking pulse. So this is called as a blanking pulse. So here the width of the back pouch is 0.09 Henries, that is 5.76 microseconds. Here H is a line period, that is equals to 64 microseconds. So here the amplitude of the back pouch remains fixed at a blanking level, that is 75% of the composite video signal. Next, after the retrace, the current in the deflection circuit reverse their amplitudes. Therefore, a small oscillations takes place in this diagram. Okay. So, because of the back pouch, the deflection circuits get sufficient time to settle down the oscillations before the next scan will start. So, here the H-sync pulses are added above the blanking level. These are separated at receiver, and after differentiation used for triggering the horizontal deflection oscillator. So here the horizontal synchronizing details, total line is 64 microseconds. In that horizontal blanking is 12 microseconds. Horizontal synchronizing is 4.7 and front pouch is 1.5 microseconds. And back pouch is 5.8 microseconds and visible line time is 52 microseconds. Next, vertical synchronizing details. So if less than this 2.5 Henries, it is difficult to separate both horizontal and synchronizing pulses at the receiver. So if greater this, the transmitter must operate at peak power for an unnecessarily long intervals of time. So for that purpose, here we are using a vertical synchronizing pulses. So in vertical synchronizing pulses, no control of the horizontal oscillator due to the entire vertical synchronizing period of 160 microseconds. So that will be overcome by using a vertical serrations. So here we use 5 narrow slats. So here in this vertical synchronizing pulses, the start of vertical synchronizing pulses, one at the end of the half line period and other one at the after a full line period, we have to apply the vertical synchronizing pulses. So due to the half line discrepancy, the triggering of the vertical oscillator at the end of the both the fields does not coincide with one another. So here we half line discrepancy will be eliminated by using a equalizing or applying a equalizing pulses. So here to overcome the drawback of the half line discrepancy, 5 narrow pulses are added on either side of the vertical synchronizing pulses. So in that we have two types of pulses are there, pre-equalizing and post-equalizing pulses. So in pre-equalizing pulses, 5 narrow pulses of 4.7 microseconds each will be added prior to the, so here we are, what we are saying, pre-equalizing. Pre-equalizing is nothing but here we have to apply the equalizing pulses before. Okay. So here we are applying 5 narrow pulses of 4.57 microseconds or applying prior to the vertical synchronizing pulses to overcome the above problem. Next, post-equalizing pulses. So here also same, 5 narrow pulses of 4.7 microseconds each are added after the vertical synchronizing pulse to overcome the above problem. Okay, so see here, total field period is 20 milliseconds. In that vertical blanking is 80 and vertical synchronizing pulse is 160. Serrations is 32 and equalizing pulses 4.7 microseconds and active field time is 18.2 0.72 milliseconds. So this is all about different synchronizing pulses in composite video signal and need of equalizing and vertical synchronizing pulses. Okay, so this is the composite video signal as per ISI specifications. Okay, so this is all about fifth lesson.